monitor's starting to wig out. Perfect. Yeah, if it starts to freak out, I'll come over there. We'll openly defy the social distancing rules. Should be on right now, shouldn't we? Isn't it starting right now?
He's going to introduce.
All right, I'm going on mute.
All right, folks. Well, we're going to go ahead and get started. Excuse me. For those of you who don't know me, my name is Erica Albrecht. I'm with HDR here in our Louisville office. Just want to welcome everyone to this last session of the Structures Virtual Partnering Conference. Just one quick housekeeping thing. If you have a question for the presenters, go ahead and type it into the chat function. That's the easiest way for them to kind of see it, to be able to answer it. And I'm just going to go ahead and turn it over to Justin and Dylan with GSI. I want to thank them for preparing today's presentation on infrastructure rehab. And so I'll turn it over to you guys.
Thank you. Can you hear me okay? All right,
yep.
Let's see if I can get this presentation going here. All right, can you see that now? All right, so today we're going to talk about infrastructure rehabilitation and the geohazards that go along with that, anywhere from major landslides to man-made structures. I'm going to kind of dive into the geohazards that we see around Kentucky, some of the repair tools we use to fix those. And Justin's going to take a deeper dive into some case studies near the end of the presentation. So in Kentucky, we see a wide range of geohazards, rock falls, sinkholes, landslides, erosion and scour due to flooding. And we can kind of break those up into two different categories, whether it be natural geohazards or man-made. So in the natural area, you've got landslides, of course, sinkholes, rock falls, and the scour. And when you start to look at man-made geohazards, we're looking at bridge abutment settlement due to pore compaction, retaining wall failures, in mines and quarries, and the hazards that are associated with those as well. Here in Kentucky, we have a pretty colorful geologic map, as you can see, which lends itself well to having a wide range of these geohazards. Makes it fun for us geotech engineers, but it creates a lot of problems as well, different varieties. Here's kind of a heat map of the landslides. This is from the Kentucky Geologic Survey. They do a pretty good job at keeping inventory of a lot of the landslides that we see. As you can see, eastern areas of the state and northern are most heavily impacted by the landslides, but they are scattered out throughout the whole state as well. Here's a picture of a rockfall project that we did in eastern Kentucky. As you can see here, there wasn't much room on the right side of the road or the left, so really no room for a catchment area. We had rocks falling on the road at this point. We were able to put nails and rock bolts and reinforced shotcrete to stabilize that. And here's a map, a heat map from KGS of sinkholes. As you can see, it's primarily in western Kentucky and central Kentucky around Lexington area, where you have the limestone and karst areas. This is kind of a cool picture. It's a project we looked at out in Missouri. This is the Cathedral of Nature. But what they've done here is they pulled all the dirt out of this area, and you can see the pinnacle nature of the limestone. And if you look at the topo map on the right, you can kind of start to see some similarities there with the circles with the inward ticks indicating depressions in the ground. So you can really see what you on the left, what you don't get to see every day. So scour is also a big problem in Kentucky. As you can see from this waterway map, we have a lot of streams and rivers and lakes throughout the state, which is great for us people that love to be out on the lake, but can cause some real problems when you get floodings, especially in like eastern Kentucky. Here's a picture of a river at flood stage, and as you can see, it's starting to cut into the roadway embankment on the left there. we were able to install a soil nail and shotcrete wall there to prevent that river from moving further into the embankment. Scour also causes problems under bridge abutments, causes the soil to be eroded away from the piers and foundations, often causing the roads or the bridges to get closed or downgraded in its load capacity. These are some more of the man-made type geohazards. We talked about bridge abutment settlement. We're all familiar with the bump at the bridge, and that's really just caused due to the challenges in construction with getting proper compaction around that abutment. We found that once water gets involved, it can go downhill in a hurry as those fines start to get washed out, and you end up with a void under the pavement surface. We also have some differential settlement problems that can occur where you have deep foundations that are more rigid, that are backfilled with a fill that begins to settle and start to see cracking and other problems associated with differential settlement. Retaining wall failure. As we all know, there's a wide variety of retaining walls that can be built. Here on the left, you're seeing a MSE wall that we repaired. Oftentimes you see problems with the pin connections in the back. Panels begin to crack and fall and displace. On the right, you can see a wall that didn't have proper drainage behind it, and soil got saturated and washed out the wall. Here's another map from KGS showing inventory of coal borings. We have a lot of old abandoned coal mines in Kentucky as well that can cause a variety of issues. The underground mines can sometimes lead to mine subsidence issues, which causing sinkholes or old mine shafts to open up at the surface. You also have some problems associated, geohazards associated with strip mining, where the burden material is placed in valleys and not necessarily compacted properly. And over time, houses get built on these filled in valleys or roads, and you start to see settlement issues and landslides that can occur in those fills. We have a lot of quarries here in Kentucky as well, and they all have their associated geohazards as well. Most obviously, you have very high shear walls and limestone that can have rockfall hazards. You can also see that these quarries often get turned into recreational areas. I think there's one in LaGrange, Kentucky that I know of, but those have to be protected against for rockfall to make it safe to the public. You can also see that these quarries will over time get filled in with water, which can begin to seep down into underground channels and cause movement in the embankments and stuff affecting the roads. So there's a lot of different technologies we use, repair technologies, to address these different geohazards. So I'm just going to briefly run through some that we use, and Justin will go into more detail on specific case studies. GSI was founded as a company on the idea of this soil nail launcher. It's basically a giant nail gun on steroids. It's pneumatically driven, but it's an old World War II cannon that fired nerve gas that was converted to fire 1.5-inch diameter galvanized steel tubes up to 20 foot long into the ground. You can see here just some pictures of it in use, but it's got a lot of benefits. Notably, it's very quick to install, and you get immediate benefit when you start to launch these nails. So it can be beneficial in emergency situations where you have a road closed and you need quick stabilization efforts. Just scrolling through some pictures here. And like I said, because it's so fast, we were able, this is a picture during a flood. This slide was beginning to progress back into the road. We were able to quickly mobilize and start launching nails and stop the slide in its tracks. And after you stabilize the slide, you can pressure inject grout through these hollow nails or tubes, galvanized tubes, and increase your bond strength even more. Speed, like I mentioned, you can get around 100 to 200 of these in a day. So in places where speed counts on, such as on railroads, where you don't want to keep the track down, or if you've got an interstate problem there, you don't want to keep the lane closed for long periods of time, it can really be a benefit in that regard. I also install a lot of self-drilling soil nails, or hollow bar soil nails, they're also known as. And these are really good for areas where you have a lot of rock, where launch nails necessarily might not work for shallow rock or big boulder fill. They're suitable for collapsing soils. It's suitable for actively moving landslides. They have high installation rates, high pull-out capacity. They have a good bending and shear capacity. And because they're self-drilling, they're suitable for both rock and soils. There's a variety of bits you can put on them, whether it be button bits if you're expecting hard rock, or cheaper clay and steel bits for soils and sands. There is also FHWA design guidance around this, and it's becoming more and more spec'd out in projects, and more of a tool that's often used. Here's a schematic of how this system works. So the bar is hollow inside, so you install a sacrificial drill bit at the end of it, and that drill bit has ports or holes in the end of it, which allows for you to pump air or grout or water or other drilling fluids while you're drilling. We commonly use grout to do it because you get the added benefit of mixing the soil around it as you drill in the nail. So here's just a picture of an exhumed hollow bar soil nail that we cut in cross section to show you. But you can see there in the center, you have a hollow bar with the grout in the middle. And then you have a neat cement grout column around that. And that's going to be the diameter of your drill bit. So most commonly 3 to 4 inches. And because you're drilling with the grout, you end up with a soil cement mixture immediately around that column, where the soil and the cement and the grout mix to increase your bond zone. You also get somewhat of an added benefit of a densified ground around that even more. Here's another view of an exhumed soil nail. You can see this was drilled with a 3-inch drill bit, and we were able to get a 6-inch grout body out of it. So you got essentially 6 inches of grout cover around that soil nail. Here's some pictures of it, those being installed. We typically use a drill mounted on an excavator. It allows us to get to a lot of hard to reach places and allows for quick installation. So there's a variety of surface treatments too that we use in conjunction with these soil nails. Here I'm showing a wire mesh surface treatment. And this works great on shallow landslides, not so steep slopes, 2 to 1, 1 to 1. And what we'll do is we'll go in and shape the slope, perform minor clearing and grubbing, drill the nails in, and excavate small divots around the nails themselves. Then we'll place down a coconut mat or some sort of TRM, depending on the sheet flow you can expect to see, to help promote vegetation growth. Finally, we'll put those galvanized plates and nuts on to suck that down on the soil and really pull it in tight. This is a desired surface treatment because it is a green finish. Over time, the grass will grow up through the mesh, and you won't even be able to tell that there's a repair there at all. On more deeper slides or slides that are steeper, we'll often use a shotcrete covering or a shotcrete wall, soil nail and shotcrete wall, where we cut down and install the nails and lifts and put a reinforced shotcrete facing on that. These can get really tall, as you see in the bottom right picture, and they are very versatile as well. We can build them out at the top to restore some lost pavement for guardrail installation. And you also get the added benefit of excavating that material off of the landslide and unloading it, taking some of the weight off and the driving forces off the slide. GCS walls is another tool we use. We commonly use it when we lose a lot of roadway and can't gain it back with shotcrete shoulder build out. And this is just a typical section and plan view of, or elevation view of a GCS wall. But Most commonly, we will install soil nails in the back to help stabilize the existing scarp and to allow for temp shoring so you can get down and work. Then we'll install some micropiles for axial support and build that back up with a GCS wall, or geosynthetically confined soil wall. And these are a little different than MSE walls in a number of ways, actually. GCS walls are composite structure, whereas an MSE wall is more of a reinforced soil structure. Because of that, GCS walls are internally stable and don't rely on the tiebacks necessarily for the stability of the wall. They're friction connections versus pin connections, so have a lower risk of failure there. They include lightweight inclusions, commonly using a non-woven geotextile fabric for the inclusions versus strong reinforcement and metal straps and tiebacks for MSE walls. We have a much closer spacing in the reinforcement, typically 8 to 12 inches, as you can see in the schematic on the left there, versus a wider spacing, 3 to 4 feet for MSE walls. And for these reasons, GCS walls have a very high vector safety and a very low failure rate compared to MSE walls. As I mentioned, the GCS walls are internally stable. So unlike MSE walls, they don't rely on the facing elements to be sound. You can take what we've done here is build a wall and peel back all the facing blocks, and the structure will still stay. And that's just due to those very tight inclusions of those geotextile fabric. So here's kind of a cartoon of when we use GCS walls and how we do it. So this is a roadway, as you can see, and then there's a slip plane that's formed that you lose over time. You have loss of pavement. And unlike MSE walls, or for MSE wall, to repair this, you would end up having to excavate much of the road out just to get enough length for the MSE reinforcement. What we do is come in and install soil nails along the exposed scarp, and then the micropiles, as I mentioned before, to stabilize the landslide where it sits. And then we'll come back and build the wall up with GCS. And it doesn't require that large amount of excavation. Here's some pictures of that in real life. You can see the slides taking out much of the road. And we came in, stabilized the scarp where it was, followed it around, excavated down to some competent material, and then installed the micropiles. You can kind of see the grade beam below those pallets there. And you can see the GCS wall now starting to come up. Here's the finished product. We added some riprap in front of it to protect it from scour, and ended up paving over this one just to prevent water from infiltrating and washing out any of the gravel. So pretty cool, neat looking project. And so here's a project we did along a stream where the stream bank was being eroded. You can see the guardrail hanging in the picture on the left there. I hadn't quite made it to the road yet, so we were able to mobilize in and drill soil nails to stop the movement and armor it with shotcrete to prevent the creek from taking out the road. We used riprap here to protect against scoured, so to prevent undermining of the shotcrete wall. It's, I guess, important to note here too, this was a rock-lined creek, so these shotcrete walls work really well when you're able to cut off down to the rock and really limits the risk of undermining. On bigger bodies of water or rivers, and where you don't have that rock-lined creek, shotcrete walls can be susceptible to erosion without some sort of other means. We've recently started installing a lot of tied back sheet piles along these. This picture on the left is along the Ohio River. But we treat it essentially as a soil nail wall. Instead of the shotcrete facing though, you have steel sheet piles. And so you get the added benefit of scour protection. So what we'll do is drive the sheets typically well below the scour depth. And that often intercepts the slide plane as well if there's one present, and increases that factor of safety as well. Then we'll torch the holes in the sheet piles and drill the nails in this picture here on the right. These are hollow bar soil nails drilled through and place plates and nuts on the end of them to secure the top of that. So when aesthetics matter, the cool thing about shotcrete is it can be sculpted to look about like anything you want it to. If you go to the zoo, you see all the exhibits, that's all sculpted shotcrete. It can be stained and sculpted to look like rock or MSE panels, even if you wanted. I think this picture here is actually in Lexington below the New Circle. Here's a picture of some sculpted shotcrete made to look like rocks, natural rocks. Another picture, so you can really make it blend into the environment and do what you want with it. So moving on, compaction grouting is another tool we use really for the more underground type problems with sinkholes or settlement, mine subsidence, those kinds of issues, or geohazards. And what that involves is driving or drilling a casing down to a targeted layer where you want to improve the soil. So in this picture, you can see the light tan layer, soft layer that's experiencing settlement. We'll drive the casing down to that and then begin pumping in a low slump sanded grout until we reach some sort of cutoff criteria, whether that be a certain pressure on the pump, a certain volume of grout, or you start to see signs of heave or cracking in the ground surface itself. And then once you get that done, at the bottom, we'll lift that casing up, typically in 1 foot increments, and repeat that process until you reach one of those cutoff criteria, until you get near the top of the hole. And when you combine this with a group of these columns, you'll end up with a treated area where you have a densified ground, which helps reduce the settlement. We talked about sinkholes. They can both be nature caused and also man-made caused due to culvert or tunnels, utilities collapsing or leaking. And compaction grouting can also be used to fix these as well. When you don't, the most traditional way to fix a sinkhole is to dig it out and replace it with rock using the filter method. But when you have right-of-way constraints or you don't want to have to close the whole road to dig out the sinkhole, using compaction grouting can be beneficial, as you can target the throat with the compaction grouting, fill it in, and then fill in the void with a flowable fill, as you can see in this kind of cartoon here. Once you have that done, you can continue compaction grouting around the perimeter of your sinkhole to fill any loose soils or voids that may have not reached to the surface. So it's a cool application of compaction grouting. Can also be used to help reduce settlement from fill loads. So a lot of times abutments will be built on soils that are prone to settlement, and over time that'll begin to happen. So rather than digging up and replacing the whole abutment, you can target, whether it be through the road from the top or down below, you can target the layers that are actually settling, compact those, densify them, and not have to replace the whole abutment. So those are some of the use cases. Here's a kind of a cartoon of the many ways you can use compaction grouting, whether it be under building foundations, slab jacking, other types of foundation ground improvement problems and geohazards. Move on to the rock fall geohazards. Here you can see a guy on ropes doing some rock scaling. And really all he's doing is knocking off loose rocks. We'll do this on every rockfall project for safety at first, but sometimes that's really all the project needs, is to go take care of a boulder that's prone to about to fall over. When you do have to go further, we have a wide variety of limited access drilling equipment. On the left there, you'll see a crane basket drill. On the right, you can see a wagon drill and a quarry that we talked about earlier. But we can drill rock bolts in and then put similar facings as we talked about earlier, whether it be reinforced shotcrete or a draped or pin mesh. Here's some more equipment we use. A pallet drill can be mounted on a skid steer or forklift. On the bottom there, you can see an air track drill. And then for very tight, limited access places, you can use handheld drills or pluggers, as we call them. for the really hard to reach places. Mesh installation on these rockfall projects can be cool to see. A lot of times we'll drop them in with a helicopter just so that we can build these long panels on the ground, pick them up, and lay them on the slope. It's much more efficient that way. And it's really cool to see in person as well. Here's another picture of rockfall. This is a pinned mesh along a railroad. You can also see a barrier, a mesh. It's kind of hard to tell with all the lines going on there, but that's got rock bolts holding back boulders, and also a draped mesh that's been pinned on there as well. So those are some of the tools we use. That was really quick, but I just wanted to give a brief overview of the geohazards we see in Kentucky and some of the tools we use to repair these. And now I'm going to hand it over to Justin, who's going to dive into some case studies that we've done around the area.
Tell me when you can see that. Not loaded. All right, appreciate it. Hopefully you can see my screen at this point. I wanted to give it a little pause there. Make sure you got it. So, a couple more beats here. I don't know, Erica, can you see the screen there? Sure. There he goes. Okay, hopefully you guys can see it now. I'm going to take you through some case studies that we've completed over the past few years, and wanted to go through Dylan's section first so we'd have an introduction to some of these tools, but I'll dive into some landslide repairs and all the way to structure repairs that we've done recently. This is a rather large landslide repair that was just wrapped up within the past year in southeast Indiana. You can see the map there. It's located right on the Whitewater River, just outside the Cincinnati area. And I guess of note here, you see the headscarp that's identified there on the left side of the screen. There's also 3 private residences that were situated right along that headscarp, as it also traversed the road there. And it seemed to be a pretty complex landslide. When we first went out there and looked at it, I saw a lot of upslope drainage coming out of upslope swales. I also saw an erosional condition down in the bend of that river, which made it pretty complicated. So you had a landslide that was driven by excess pore pressure in combination with continuously eroding toe and loss of that passive resistance. So it's a pretty fast moving slide and very, very large. As you can see, it's about 2,100 feet long there along US 52, and then measured along the center line of the road. And then if you were to measure from that peak up the hill down to the toe, we approximated it at about 275 feet. So a pretty massive landslide, a quick mover, and it was right after a lot of the rains we had in the spring of 2019. So these are some ground level shots you see on the left. This would have been the left side of the previous picture we were just looking at. I've painted the road there to show where this slide has crossed and is trying to rip the road in half, and the headscarp is heading up towards those houses in the distance. And then on the right hand side, you see the terminus end of the other side of the slide. So and that's following the center line and then working its way up that driveway in the distance. So it took quite a while to map this slide. You see some of the photos of the headscarps right up above these people's yards, traveling along their driveways on the right. You just a massive slide occurring pretty rapidly, and some of the homeowners actually experienced some displacement of their footings. In the house, the structures were quite a bit of distress as a result of the landslide. A pretty urgent condition. We partnered with NDOT to work through a proposed site investigation. This consisted of 24 standard penetration test borings and 10 inclinometers. We also did a series of grain size analysis, Atterberg limits, and unconfined compression test to try to better define the bedrock profile and understand this residual strength and that were still remaining after the slip occurred here in those soils. You see on the right the boring location plan showing some of the locations of our critical cross sections with those white lines running from right to left. So after observing the inclinometer data for a few months, we did do this study concurrently with the landslide repair due to the urgency of the slide. So we were gathering data and working on the design simultaneously. And so you can see, you'll probably notice the construction photos overlap these inclinometer readings. But we did make one consistent observation that the slip appeared to be occurring right along the contact of the weathered shale and competent shale bedrock layers, indicating a pretty deep-seated landslide there. And we also noted, a need for drainage improvements through improved ditching to promote the water flow out of this landslide. We noted that you may or may not have noticed there was a highway and a railroad below, so the drainage was getting caught up in various locations as that railroad had been abandoned over time, leading to a pretty saturated condition. We also noted that the scour in the bend of the river was likely to continue. We also had overhead utilities to contend with that couldn't be moved in a timely fashion as fast as the slide was moving. So just a very rapid team response was needed to prevent this from taking that road out. So when we first started gathering information, we took the survey cross section we could in the field in conjunction with LiDAR data, and then of course the geotechnical information provided by NDOT. And we noticed the bedrock profile is fairly consistent upslope and kind of dropped out towards that worst part of the slide. We did a sensitivity analysis trying to model the existing condition of the slope. You can see on the left, we call that a back analysis. We ran that using the normal groundwater table. And then on the right, ran it again using that elevated groundwater table to model the excess pore pressures coming off the hill. In the end, we partnered with NDOT to come up with a design consistent of a three-tiered soil nile wall with 3 different facing elements. The top wall would consist of a high-strength galvanized mesh facing that Dylan showed previously. That was to control an intermediate slide condition that may be present, and also to prevent further clogging of those ditches on the inboard ditch. And also it's a more green look for that upslope for the traveling public. The middle wall was to consist of a 12-foot shotcrete wall starting from top of pavement, measuring down 12 feet. That was to really start to stabilize the slide. And then the buttress wall, the low wall on the riverside of the railroad, was to consist of a anchored sheet pile wall with long nails tagging bedrock, and each one of those would tag rock, and that wall would provide the scour resistance needed as well as some much needed buttressing. So this is a cross section showing the proposed repair analysis. You can see through the addition of the 3 walls, there's a pretty high factor of safety right through that road platform of 1.6 or greater. We also studied the original slide that peaked up above those homes. They were able to get a 1.3 factor safety against global instability there for that extreme elevated water condition. So we monitored the inclinometers throughout construction, and as an engineer, it's always interesting to run your models and hope they're going to be reasonably accurate, but it's nice to have the data to check it against during construction. So if you see on the right, the photo on the left is the initial lift of nails going in. You may be able to see that along the far left and into the distance. On the right-hand side, you see the inclinometer. A lot of movement has taken place from the initial installation to, where you see that green line. There was a reading right before we started work. And this photo was taken on 8/13/20, so somewhere in between those two readings. This photo was taken on the 23rd, so the same day as that reading. You see that movement starting to slow. And if you remember from our back analysis, we had a 1.0 to 1.1 factor safety with just the two walls installed, so that would imply the slide would slow to a stop. We got the middle wall completed here, and you see the movement start to creep down to negligible there towards 9/11. This should have been a 2019. That's a typo. So it implied that nail was working, or that wall was working just as designed. So that was good. So just another look here at the boring plan to remind you of the locations of RB3 was right through the worst section of the slide there near the top of that boring plan. This is an image of the pin mesh wall that was constructed, working around the more mature trees. And, this was right after it was constructed. Now it's covered in more vegetation. Picture on the left is the impact hammer that was used to seat these piles. Of note here, we did take a drill rig and walk along the sheet pile wall to, number one, get the depth of bedrock so we can order the exact sheet lengths that were needed. And then number two, to try to perforate that rock so we can punch through it with this impact hammer and seat those things in the bedrock. So you see that hammer on the left doing its work. And then on the right, there's a couple rows of finished nails that are being installed there through the facing. This is an overall aerial imagery of the site. You see I might have a video here. See if this will play. Okay, so we did a drone flyover probably within the past couple weeks. So this has been 6 months. Had time to grow some more vegetation through that upper wall on the right. You can see the pole foundations are pretty unique around these. I call them planter boxes, but we built a foundation around the pole to let them remain in place. You can see the new culverts that have gone in at each of those upslope swale locations. And there's a corresponding pipe that goes under the railroad track there to also promote that drainage away from the slide. So just an overall view of this one. So, moving on, this is another landslide that has impacted a structure. This is in Eastern Kentucky. You may or may not be able to really see it from this picture, so mapped it here in the aerial. You can see the headscarp is right off the end of the bridge. And there's a couple different, there's a toe bulge there that's above another headscarp, so a couple intermediate slides. We did go out and investigate this site with some rock soundings so we could further understand what was going on with that progressive slide right in that location on the corner of the bridge. This was the back analysis that was modeled on that slide. The roadway surface on the far right, part of those orange circles there, and extended on down. So this further kind of backed up where we mapped those scarps out in the field visually. So you see the two critical scarps are right in line with what we saw out there. So this repair, we proposed, I think it was a 14-foot soil nail wall with, you see 4 rows of nails modeled up in here in the top. I've got the surcharge load on there. It's just right at that bridge abutment. I've created a long stability bench to push those failure surfaces away from the structure, and then leaving a 1.4 factor safety below our wall and a 1.7 through the road platform, which we considered acceptable. Further complexity on this project, you see on the top middle part of this plan, those are grout holes for compaction grouting. Dylan introduced that concept earlier. We were concerned that the slip might have pulled away from the bridge and caused voids back in behind the back wall, and recommended the compaction grouting as part of the fix to restore the active passive pressure behind that bridge there on that downhill grade. So you also see the wall alignment here, parallel in the center line of the road, and then kind of following the scarp off to the right, terminus point there. So being in Eastern Kentucky, you never know what the roads were built out of. So when we made our excavation, we found some decent sized boulders in the cut. Continue to work through that in a top down fashion. Guardrail was able to remain in place, as you can see, and just continue to carry this down using a reinforced shotcrete facing, as we discussed before. This is a finished look of the wall. Just taken them more recently so you can see what they look like farther down the road. Another bridge in Western Kentucky. This is a scour-induced failure. It has flanked that wing wall that's hanging in midair. The slope used to roughly follow. You can see kind of the soil marks along the wing wall and kind of imagine the original slope condition. This was after, I think, the spring rains, either last year or the year before. It's undermined the road and had that lane closed. So this was a fairly new bridge constructed in 1992, 318-foot long span. It was a curved bridge with a significant skew, and it had experienced some post-construction settlement of the approaches and some stability issues. There were wet years in 18 and 19 that contributed to the scour that we noted there and caused that short corner to fail. So KYTC Geotech came in and did a geotechnical investigation and encountered soft soils with saturated foundation conditions. They reviewed that original geotechnical report and found some changes they wanted to make to the slope stability analysis, and then recommended some possible corrective actions, one of which was soil nailing. They also investigated lightweight fill, an anchored wall, and some other options. Concluded that the soil nailing was the most cost effective. So we proposed to build a 16-foot tall wing wall parallel the center line of the road, and then put an 8-foot extension of the back wall below the bridge, working under the existing deck. And then we chopped off that wall that's hanging in midair there that exists, the original wing wall. So this is a typical detail of the bridge. Under the bridge, you see the horizontal drains that have been installed to help promote drainage out from behind the back wall, restore that, and then we've put a riprap revetment down for further additional stability. We formed out the soil nail wall to regain a couple feet of shoulder, and then backfilled that with a lightweight engineered fill, and then of course carried that riprap revetment around the toe. It's the finished look of the wall with the wall chopped, or the wing wall chopped off, and the completed view. Another structure in Western Kentucky. This was closed. It was over a CSX railroad track and led into New Salem Loop there. The city owned this bridge, and it was built in 1988. There were pretty shallow depths of bedrock. They were visible at the base of the railroad track at about track level. The foundations consisted of short pre-stressed concrete piles bearing on bedrock. There were bridge inspection reports that had noted the erosion and other issues of the slope. We also noted that the railroad had built a track siding under the bridge back in 2015, and that large retaining walls were installed around 2011 to help stabilize those slopes. And then portions of the walls were removed in 2017, followed by a water line failure later in 2017. And then those walls under the bridge were removed with the soldier and replaced with a soldier pile and lagging wall later that year. Following additional subsidence, the structure was closed November of 17, and then we started looking at repair options, and ultimately decided to make the repair using micropiles and soil nails. So if you look in the picture on the left, you see some stress cracks right under the cap that, to me, implied that you had the cap was braced, and you continue to have earth pressures push into those piles and start to overstress them, causing the cracking that you see there. Looking at the photo on the right, the obvious rotation of the cap has moved and overstressed those foundations. So the solution, you see schematically here, the top in the elevation view, we'd propose to build basically a sister cap around the existing cap, construct battered micropile foundation, and weave that in between and behind the existing pre-stressed piles. To provide additional rotational strength, we brought in a wagon drill, which Dylan introduced that in the rockfall segment. Use that to drill under that bridge abutment with almost no headroom and put a rock anchor in to tie that system together. This is a finished view of the bridge right before, I think maybe right after opening. And the view of the cap. Overhead view. We've already covered this at the 3 o'clock session. I know the Weisenberger Mill Bridge was covered in detail, so I can go pretty quick given all the background was provided there. Hopefully you got to see it. If not, this was an existing stone foundation, Weisenberger Mill on the right, and then a single span pony truss bridge there. Here's the specs on it. It's built in the 30s, 72 feet long, just downstream of a dam. And then, of course, the abutments were historically significant limestone, but there was significant deterioration that caused some corrective actions to be taken here. So in plan view on the right, that was the abutment that was nearest the mill that had the most distress. We installed a series of micropiles around that shotcrete reinforced skirt that we built. And then you see a series of soil nails that went through the existing masonry abutment using those injection anchors that Dylan introduced previously. So we were able to backfill some of the voids behind that while we were drilling the nails. And the micropiles doubled as scour protection. Also, they carried the additional dead load of the shotcrete jacket that we put on there to help with that bridge structure rating. So if you look, here is an elevation view on the right again. It's the abutment we were just discussing there. We installed some cased micropiles behind both of the original abutments to serve as the new bridge foundations and transfer that load to competent limestone bedrock. They were 5.5-inch diameter cased micropiles. So something that we worked with KYTC to come up with a design that we had the materials on hand and could quickly get it built. Here's a side view of the wall. The picture right before that deck was placed, or right after it was removed. Picture with the nails going through the abutment. Drainage strips, reinforcing steel. Here's your cased micropiles going in. And then kind of a pano view right after shotcrete went in. Give you some scale there. Here's a picture right after the span went back in. For the last case study, I think I have 2 minutes left, so I'll breeze through it here. This is a deep-seated slide in eastern Kentucky that had taken out a segment of the road platform. This is a LiDAR image that we were able to take with some of our drone technology and get a better feel for just how massive the slide was. You can see it starts in the upper part on State Route 74 there as the route bends around the horseshoe, comes down and toes out down there on the bottom part of the wall. Rotating the cartoon for effect there. So this matches up fairly well with what we noticed in KYTC LiDAR imagery, which is a tool we use frequently to help identify how old some of these slides may or may not be, and some physiographic features we might be able to observe too from those. And then you look on the right, there is a GCS wall that we've modeled in to restore that road, along with the soil nails and micropile supports, similar to the concept that Dylan introduced previously. So similar drawing to what you've seen, reinforced soil nail wall in the back to stabilize the remainder of the roadway. Micropiles installed to transfer the weight of that GCS wall past that slide plane and into bedrock. Some photos of the construction. placement of the GCS. And then we added a splash pad there below that culvert to help with dissipating that energy. But that's all we got as far as the presentation. We should open for questions. It says it can't hear me because I'm not transferring signal. But it's possible people can hear what we're saying. So I don't know what's going on.
I can hear
Nobody coached us on what to do now.
I hear us. No one has any questions.
All right, so I think they hung on through
There you go.
450, so we're good. Who proposed the invent placement? Oh, encasement. So that was a design recommendation. We partnered with KYTC Structures Design Branch to actually do the structural design on that bridge. We only provided the foundation recommendations that were checked also by KYTC. So we kind of consulted on constructability and provided some conceptual design input, and then the structures branch finished with the final design.
They come up with a more global solution for settlement at bridge ends, or even discussions with structural design to come up with a fix during construction to avoid issues down the road.
Where do you see that one?
Click on the Q&A.
No. We've talked about that for several years. There's been discussion of using GCS to help transition that. You can vary the thickness of, being thicker towards the back of the bridge and feather that to nothing there off of pile supported bridges. I know that's something KYTC's been discussing. I don't know how many they've implemented, but that's something that we've seen. We've seen lightweight concrete's used. The compaction grouting, something we've used in Ohio and some of the surrounding states. I think even in Kentucky, we did one in Louisville last year to help fix some of those bumps at the end of the bridge. We did one in Frankfurt 3 or 4 years ago to fix a void under a approach slab. So the compaction grouting gets a lot of play there, and then so I would say also the GCS on newer constructions where you have a road outage.
Is the compaction grouting similar to mud jack?
Yes, it is. Mud jacking is kind of the end of the process. So compaction grouting, you want to target the source and the symptom at the same time. The symptom can be fixed with mud jacking. Usually, the symptom is settlement, but the source of the problem, is usually some softer layer that's deep seated under the embankment fill, and you can target that, compact it laterally. So a lot of times these fail because they couldn't get good mechanical compaction during construction from a sheep's foot roller doing that vertically. So we come in with grout and laterally compact that using a primary set of holes, and then coming back in between those and secondary and possibly tertiary holes to mechanically compact that laterally after the fact, surgically. And then as you pull out of the hole, you change the rheology of that grout to be more of a slurry. And then you mud jack to lift the slab back into its proper alignment. So it's all done kind of on the fly during construction as you're extracting your casings. Yeah, thank you for the question. I don't know if we covered that in detail. Thanks, Mike. Well, great. I appreciate everybody jumping on and, available anytime anybody has any questions to follow up.
Yeah, thanks again, guys.
All right. Do we sign off or what? It says up here, don't end the webinar. Pretty clear.
It's gonna end in 4 minutes.
There was one question at the very top that said a scuba diving resort in Hopkinsville.
Penny Royal. Penny Royal. It's cool.
Thanks, Aspen. Well, we got the pleasure of doing the final presentation of the end of the day on the afternoon.
Get out, I guess.
All right.
Click on more over there on the right. You can just click exit webinar right there.
All right. Thank you all. I'm going to log off now.